Today, I will be presenting our work on solving threat alert fatigue problem that exists in large enterprises. This is a joint work with NEC Labs and Virginia Tech. So data breaches are becoming worse every day. This chart shows that how many data breaches happen for different companies in different years. And as we can see that the total number of breaches have increased in past few years. Today, the goal of every company is somehow to keep their name off this chart. And the way that they achieve this goal is to deploy threat detection softwares. And these threat detection softwares continuously monitors organization-wide behavior and generate any sort of threat alerts if some suspicious activity happens in your organization. But it is very well known that these threat detection software generate a lot of false alarms. A recent study shows that these organizations receive more than 10,000 alerts per week, and 51% of these alerts are just false alarms. And only 4% of these alerts are actually get investigated because they don't even have enough resources or staff members to go over each alert. And in the end, they waste more than 1 million every year just to respond to these false alarms. And because of this large number of false alarms, they face a problem which is known as threat alert fatigue problem in the industry, where a cyber analyst or security analyst cannot respond to the threat alerts because they receive so many each day. Now the question is why these threat detection softwares generate so many false alarms. And the answer is that these threat detection softwares are based on single event matching rules or heuristics. And in most of the cases, they don't have enough context to actually separate a false alarm from a true attack. For example, if you have a rule that says that if a process reads and writes a lot of files in a short span of time, then generate a threat alert. This rule is to catch ransomware behavior. But a lot of benign applications, such as compression utility, also shows this behavior. Now, if you are running program 1 and program 2 in your system, both of these programs will generate a threat alert. However, if we look into the contextual information of these programs, we can see that the program 1 came from an email attachment, which is a sort of a rare or suspicious event in your organization, while the program 2 came from a Windows updater, which is a commonly happening event. And based on these contextual information, we can say that the program 1 could be more likely to be a malware, while the program 2 could be a compression utility. So this is the key idea of the NoDoze, where the suspiciousness of an individual event is informed by the suspiciousness of its historical context. And using this contextual information, we can better triage the threat alerts, essentially preventing the cyber analysts from falling asleep on their desk by giving them a NoDoze pill. So in order to generate this contextual information, we use data provenance. And data provenance is essentially the detailed history of your system execution, where it is usually represented as a graph, where the vertices are the sockets or processes, and the edges are the causal dependencies between these objects. And it is usually represented as a three-tuple where it has source, destination, and the edge relationship type. And these graphs are really helpful in alert or attack investigation. For example, if mal.exe is making a suspicious connection to malserver.com, you can use these graphs to find out from where it was downloaded, where the mal.exe was downloaded. So now we have created these contextual information. Let's see how NoDoze use this information to triage the alerts. So first, we will collect the data provenance from organization, from each host in the organization into a central repository. Then an underlying threat detection system will parse these logs and generate threat alerts. These threat alerts are then ingested by NoDoze, where for each threat alert, we will generate a provenance graph. And then on top of these provenance graph, we will perform 3 steps. First, we will assign anomaly score to each event in the graph. Then we will propagate these scores to our neighboring events. And finally, we run our graph reduction algorithm. In the end, we will present us a sorted list of threat alerts with their contextual information. In the next few slides, I will go over these three main steps in more details. So first, in order to assign anomaly score to each event in the graph, we will build an event frequency database. This database essentially encodes the typical behavior of your organization or enterprise. Then we will generate a provenance graph for each alert that is being triggered in your enterprise. And then we will assign transition probability to each edge or the event in the graph. Essentially, this transition probability encodes that how often an information flows from a particular source to a destination with a particular relationship type. And it is calculated by the formula shown on the slides, where the numerator basically accounts for how often data flows from source to destination, while the denominator accounts for how often the data flows from source to anywhere. For the purpose of this talk, let's say we have only two transition probability, the high transition probability of 0.8 and the low transition probability of 0.2. So once we have assigned these transition probability to each event, we will propagate these scores to the neighboring events. For that, first we will generate all possible paths for our graph. In our example graph, we had 4 possible paths, and for each path, we will generate a regularity score. Beside the transition probability, this regularity score also takes in and out score. These scores essentially accounts for total amount of data flowing in and out of the source and destination. Or in other words, it signifies the importance of the vertex as an information producer or a consumer. For this talk, let's consider that the in and out scores are essentially 1. And by using this regularity score formula, we calculated the score for each of the paths in our graph, as shown on the slides. Now, the anomaly score is essentially 1 minus the regularity score, and we calculated the anomaly score for each of the paths, and it is shown on the slides. Finally, when we have assigned anomaly score to each path in our graph, we will combine top k paths and merge them together in a subgraph and generate an aggregate anomaly score for that threat alert event. And in the end, we use this aggregate anomaly score to triage the alerts in your organization. So once we have triaged the alerts, we also want to accelerate the investigation or forensic analysis process. And data provenance graphs are very useful in doing that. But the data provenance analysis essentially suffer from a problem of dependency explosion problem. Essentially, in this problem, an output event is falsely assumed to be causally dependent on all preceding input events. For example, in this graph, if we try to backtrack from a malware process node, we will end up with 3 false dependencies or irrelevant dependencies. All the existing solution to these dependency explosion problem require either instrumentation or developer intervention. But for our case, we propose a new idea of behavioral execution partitioning, where we partition the graph into a normal behavior and an abnormal behavior, and essentially remove any sort of normal or paths from the graph. In this case, if we had one highly anomalous path, we will just consider that path and prune all the other normal paths from the graph, essentially reducing the graph by a substantial amount. So we evaluated our NoDoze system in NEC lab using a commercially available threat detection software, which is known as NEC-ASI system. It had around 200 hosts, and we populated event frequency database with 1 month of data. And we generated 364 alerts by their underlying threat detection software. And in this 364 alerts, we have 52 alerts, which consisted of some of the famous attacks that we also saw in the previous talk, such as WannaCry attack. And we also generated, it also generated 314 false alerts, which were validated by the analysts. And in the summary of our evaluation, we found out that we can reduce 84% of the false alarms in our evaluation. Similarly, we can save more than 90 employee hours by not responding to these false alarms. And our provenance graphs for investigation are 2 orders of magnitude smaller than the existing solutions. So the main purpose of the NoDoze system was to triage alerts, but we also set out to see, can we exclude some of the false alarms from the consideration. And after ranking, we used a separation threshold to figure out how many false alarms that we can remove. And using a separation threshold, we found out that we can reduce 84% of the false alarms with 100% true positive rate. Then we also want to measure that how much time we can save by not considering these false alarms. So we did a literature review and find out that analysts usually take more than 20 minutes on average to investigate each threat alert event. And in our data set, we had 314 false alarms, and by reducing these false alarms by 84%, we are essentially saving more than 90 hours. Note that our enterprise had 200 hosts. So if you had a larger enterprise, we can essentially save a lot more time than 90 hours per week. Similarly, we simulated a WannaCry attack in our enterprise, and this is a graph for the provenance graph of that attack. In this attack, we also got a true alert and a false alarm. But by using our behavioral execution partitioning technique and removing any sort of benign paths from our graph, we show that our graphs are much, much smaller than the existing provenance graph for the WannaCry attack, and it does not sacrifice any information that you need to actually investigate the attack or finding the root cause. In conclusion, we developed a threat alert triage and investigation system, and this shows that we can use historical information and contextual information to improve state-of-the-art threat detection softwares. And finally, our evaluation results shows that we can substantially reduce the slog of investigating these false alarms in enterprises. Thank you so much, and I'm happy to take any questions now.
Hi, Maria Postolaki from ETH Zurich. Thank you for this talk. So I was wondering whether this is something that you can do online as well, or is it just supposed to be offline?
Yes, we can do that online. There is nothing that stops us from doing offline.
And what is the delay that I should expect from the time that the alert is creating until this process is done?
Sorry,
or
say it again?
does it depend? So my question is, what's the delay between the time that the alert is creating until you can actually do something?
Right. So in our paper, we show that it takes around 200 seconds on average to do this analysis and triage the alert.
Mm-hmm. Thank you.
Thank you so much.
Hi, so a question about this. So when you were comparing this solution, your reference of comparison was a device or a CM solution?
What do you mean?
So CM is managed security product, which would do a lot of what was described here. Or did you just measure a security appliance that's producing alerts randomly? Not randomly. Basically, it would raise any alert that it sees.
So basically, this was a commercially available threat detection software that NEC uses, and it has event matching rules or heuristics that if it sees some sort of a suspicious behavior, it generates an alert.
Yes, but these days not everything works on just on rules. So the other question, as per the reduction of raised alerts, what were the scores of alerts that were unnecessary in the reference solution? So basically just asking if your point of reference would score these alerts.
Right.
Would be just simple to remove the low scored ones.
I don't know if I understand your question. Can you repeat?
So yes, not all alerts raised by security systems are of equal importance.
Okay, okay.
Right. So when you were comparing, what were you comparing with? Something that is, let's say, in a simple security device, a block.
We take all
the
level of
alerts.
alerts. There was no severity difference between any alert. Even if the severity level of that alert is low, we will also consider that.
Okay, and the last question. So one of the reasons why you would still present something that may be a false positive is to address lack of visibility. These threads that you were producing, did you have any measure where you would have very limited visibility as saying, okay, this file came from this source to this source and this basically downloading software was used and you don't know anything else?
So we treat the
Would you
underlying
push that
threat
out or
detection
no?
software as a black box, right? So it doesn't matter. It does matter, but we don't see how we don't take into account of the false positive, false negative rates of the underlying threat detection software. Is that what you were asking, or?
Roughly. Thanks.
Okay, I will take it.
Okay.
Time? So what it wasn't clear to me is how much training you actually have to do to learn like what is actually like typical or not in, and how specific that is to the enterprise that you're actually like studying. Because it seems like, I mean, in my experience, there's a lot of events that are uncommon but not malicious, okay? And then at that point, you might be able to filter some things because they were common, but maybe what you are not filtering is still too much, right, for the analyst and that, and how much that actually depends on the specific enterprise.
Right. So that's an excellent question. So even though one part of your whole progeny or ancestry of the events is uncommon, we look into the whole path, right? So how did that event ended up, or how did that process ended up in your system? So that typically removes this sort of bias that even if you haven't seen one process, but by using our network diffusion or propagation algorithm, we can essentially build a much more confidence that overall this process should be more suspicious or less suspicious. So even at one event level, it might look like this is uncommon, so it should have a higher anomaly rate. But when you look into the progeny, the ancestry of the events that led to that particular event, you can make a more confident analysis that this is essentially not anomalous enough.